I think we're going to start. So I'm really pleased to introduce Dr. Vivó-Truyols from the University of Amsterdam. I want to notice the very interesting topic here because there's been a lot of discussion about whether the Bayesian network methods can be really used for the real scientific work, whether it be the biological analysis, chemical analysis, and so forth. So it's interesting to see someone who's going to talk about that exact difficult issue. Controversial, say.
Yeah, thank you very much. Can you hear me? Yeah.
No.
You can, I'm pretty sure. So thanks for your introduction. In fact, I must admit that the first time I was introduced by the INI and to just get a little bit pushed to come here was through Marjan Sjerps, and the first time I was really scared because you told me you can go to the INI Institute of Mathematics, University of Cambridge. I say, oh, this is very scary. I say, I'm not a mathematician, I'm a chemist, and sometimes I'm very scared to talk in front of mathematicians because they can tell lots of things that I don't understand. But the first time I came, what exactly the atmosphere that you were pointing out, saying, oh, I just met botanists, I met chemists, I met physicists, I met computer scientists, I met lots of people, so it's really a multidisciplinary environment. I say, okay, I feel comfortable now. I'm not a mathematician, I'm not a physicist, I'm a chemist. And in fact, I put as co-authors several people, including you, Marjan, because I'm going to talk about certain things that we did together. And that's kind of my initial introduction. My initial introduction is that, well, in that sort of team we had a forensic statistician, Marjan, Lopatka, artificial intelligence, somebody from engineering, a telecommunication engineer, so Andrei is a doctor to be, so hopefully in March next year he gets the PhD. Michael, he's an epidemiologist, and me, last one, I'm a chemist. So it's a kind of soup of people. I just said, okay, that looks like a soup of different people putting together. In fact, it's not the 4 Max brothers, it's the 5 Max brothers. So everybody in this soup, everybody talking a different language, everybody talking about different things, and we start to have some fun. I mean, not everybody has been involved in everything, so it has been kind of sub-teams. So Marjan and Martin has been working together with me a lot. And then I've been working a lot with these 2 PhD students. Marjan has been involved a little bit. So, but the thing is, the language that we speak, we started to discover several interesting things. So, think about a forensic investigation, for example, a fire. So there is a fire somewhere, you want to investigate what has happened. And the first question that arises is, what's the evidence? You think about, in general, that's a philosophical question almost, because the evidence is exactly the crime scene. The whole crime scene should be the evidence, right? So that's not doable because we cannot analyze the whole crime scene, so I have to take samples. There was a nice lecture in the previous seminar by Peter Verheer about the fact that we have samples, but we cannot analyze everything. So we have to select some samples and analyze some of the selection of the samples. I had some interesting consequences from the calculation of the likelihood ratios. So we take samples from the crime scene, for example, from the suspect, or from anywhere. But that's not the evidence. The evidence is not the pot that arrives to the lab. The evidence is the signal generated by the instrument that analyzes this pot. Okay, and lots of things can happen there. I'm going to discuss that. And even after that, sometimes people think that the evidence is the relevant peaks or relevant signals found after this has been analyzed in the lab. And we started to think along these lines, saying, can we start to think in a Bayesian way a little bit earlier? Because we had some kind of very nice discussions together. So sometimes mathematicians or artificial intelligence people call the lab sort of a data generating room, meaning that I don't know what's happening behind. It's a door that I don't want to cross. Something happens there, generates data, and then we do the analysis here in Bayesian way. And we chemists sometimes like to talk to the data analysis people like the data crunching people. We don't know what they do, which is produce a table of numbers, and they do some magic there, and that's great. We wanted to break these walls, so we started to think about, can we push these people inside lab and see what's going on there, and also can we get the lab people inside the computer people and try to discover what's going on there. So kind of breaking this wall and starting to talk about labs, things that happen there, and data analysis people as data analysis people, not just kind of magic or data crunching. So the first example is fire debris. That has been mainly the thesis of Marjan Lopatka, one of PhD students together with Marjan. And I'm not going to talk about whole thesis of Marjan, of course, but I'm just going to talk a little bit about one aspect he has been doing. So he has been analyzing flame accelerants in fire debris, so saying the question we want to answer is has this fire been provoked by somebody, so somebody adding gasoline or diesel or kerosene or something in a corner of a room and then setting fire to that, or was this fire not provoked, basically. And we analyze these via a very complex machine. In the instrumentation we call these two-dimensional gas chromatography. For the people who's not chemists, what happens here is we separate the hydrocarbons in terms of their volatility here and in terms of their polarity in these axes. So if we analyze a sample that has been used to set up fire, we expect to have some profile of the hydrocarbons that have been in the sample. They are pyrolyzed, there's lots of process that happens in the fire, but still we can find traces of hydrocarbons in the sample, basically. So if we think Bayesian, and we think along the lines that I explained before, the evidence should be the whole data set that we have here. Okay, so we really have to calculate the likelihood, and you have to calculate the likelihood. This is going to be the evidence, but we have the first problem. This evidence is 1 gigabyte of data per sample. So if we consider every single point here, we have millions and millions of variables that we have to model inside here. And maybe we have just one sample. I have to model the denominator of the likelihood ratio, of course, in the forensic context. So we need a database, but still, the database is not going to have millions and millions of data points. So we really cannot model this probability unless we do some assumptions. We have to do a massive variable reduction there. That has been part of Marjan Lopatka's thesis, and we have also other problems. So not only the fact that we have millions of variables inside there that we have to model, but the fact that when we have two samples and we inject these two samples in a gas chromatograph, these two samples, even if they are the same, have the same peaks, the peaks are misaligned. That's normal. It's not because we are bad chemists, that's because the instruments are like that. In a gas chromatography, this is a time, so compounds travel through a column and they arrive to the end at a certain point, and this is impossible to repeat exactly in the retention time for the next injection. So we always have misalignments, and we have to deal with that. This is the data that we have. It's not that we are bad chemists, it's because this is the data. So what Marjan did in one of his chapters was to propose and do some sort of variable reduction, a massive variable reduction. The first step was to take areas of this GC chromatogram, and within every square we sum all the data that's in there, meaning that we lose resolution. And now the resolution of my machine is going to be a lot lower because everything that is in this corner, that might be different hydrocarbons together, we put together in the same pot. It's reduced to a single variable. Okay, it's not 10 variables now because we have a third dimension here, because that's mass spectrometry there, so we have maybe 10 times 700, so 7,000 variables. So we reduce millions of variables to 7,000 variables, but it's still not enough. The next is to select the most relevant channels. We're using a technique. I'm sorry that I missed Daniel Ramos' lecture yesterday, but he's the expert in these. So we wanted to apply CLLR, basically which channels are most penalized because of the fact that we have false positive, false negatives. Okay, so we select the best channels based on the CLLR objective, and then later on still we have too many variables, we project them via LDA. Once projected via LDA, we pick up maybe 2, 3 loadings, and then we remodel the population of the projected scores. All these, of course, inside of massive cross-validation, because there might be information leakage here, so we just set up samples out of the calibration data set, and we do the whole variable selection here, and then we test how the method works with the validation data set, of course. In the end,
Remind me what LDA stands for?
linear discriminant analysis.
Okay.
Sorry, yes. So it's like PCA, but the directions are found to maximize the between variance and minimize the maximize the between variance and minimize the within variance, basically. So in the end, we arrive to something that has maybe 2, 3 variables. So it's easy to model, and at the same time, via this massive cross-validation, we were able to reduce variables, select variables, and project variables. So we arrive to, it's not pure variables because they are scores, so there's a mixture of the variables that are found here, but it still is a good reduction. So the first lesson is saying, what we are doing now, what normally people do is saying, with all this process, they don't care about Bayesian till the very end. So they have GC analysis, they just do whatever they do, a pig table where they select only the things that are relevant here. They select a pig table, and then with the pig table, which are only certain hydrocarbons, they do the Bayesian analysis. What we do here is something different. So we take into account the Bayesian analysis from the very beginning. So we do of course a variable reduction, but we have the eyes put in calculating the likelihood with raw data instead of calculating the likelihood with a pig table. So basically, we try to push the way of thinking in Bayesian way from the lab perspective, not only the data analysis. So we try to break these walls, saying, people do something there, present me a table of data, and then I'm going to do Bayesian analysis later on. We don't want that. We want to push the Bayesian analysis at this step. That's mainly the main message from my talk. Another thing that I've been doing, not completely related with forensic, but can be applicable to forensic, is how, again, to analyze these big tables. And that's been a very interesting example of how we do the wrong thinking, basically. There was a nice lecture, I don't remember the name, an Italian guy saying, yeah, here, what's the truth? You mentioned in your last seminar, what's the truth? And we cannot know the truth. And in fact, everybody, when analyze this type of data, they do a kind of peak detection in which they select the most likely answer, but not taking into account all the answers that might be there. And I'm going to explain this in a very simple example. This is 2D chromatography. This is in fact corn oil. It's nothing to do with forensics, but it's still the exercise of thinking in a Bayesian way helps. So as there's been a separation of corn oil in 2 dimensions. Sorry for the ones that are not chemists, but we have a silver column here. The silver column separates the fatty acids in terms of the number of double bonds that you have, and this separation separates the fatty acids in terms of the polarity. So we can see the whole map of fatty acids in a corn oil or any natural oil that we have there. And when we analyze these data, we know that certain peaks might be merged because the peaks belong to the same compound and belong to the same compound. These are individual peaks. And we have a problem about merging. Basically, we have to calculate the amount of these fatty acid and the amount of these fatty acid. So meaning that there is a peak here and a peak here and a peak here and a peak here and a peak here that belongs to the same compound. There's a peak here and a peak here and a peak here that belongs to the same compound. There is ambiguity there. This is where I want to go. So we have 2 ways of merging these peaks that do not break rules of chemistry, basically. We know that peaks should be unimodal, so it goes up and down. This also goes up and down, and should have some sort of a Gaussian shape. They both have the same conditions, and this is where we are starting to break the common way of thinking. Any software that performs peak detection is going to give you just one possibility. It's going to give you the most likely answer, and it's going to forget about everything that is behind. We started to think differently. We want to provide a solution that takes into account all possible scenarios and weight them in terms of their posterior probability. So in order to think along these lines, I just started to think about the possible peaks that are detected in the 2D chromatography and tried to start to think about all possible solutions, all possible peak arrangements in these scenarios. There might be more than 2 peaks, there might be 3 peaks, there might be arranged in different ways. And we discard some solutions that the prior probability of these solutions is too small to be considered even in the process of Bayesian thinking. So the prior is going to be 0, so who cares about likelihood? The posterior is going to be 0. Other things, the prior is not 0, so we assign the same prior to everything. That is possible, basically. And the next step, we just calculate every single possible scenario, and we think this in a Bayesian way. So we do some approximations. We don't want to calculate the whole thing because in the end we normalize, so don't care about this term. The second thing is we know that our priors, or let's say we don't know, but our state of knowledge before considering the data is just flat, saying I give the same opportunity, the same probability, same prior probability to every configuration, and I arrive to the fact that my posterior is going to be proportional to my likelihood. And that's kind of very nice likelihood, simple and nice, but you know the story about calculating likelihoods is not like that, because you just need to calculate likelihoods and you have to marginalize of different parameters. I'm not going to explain what is that because it doesn't matter. The story is that this starts to grow and grow and grow, and they have to consider also other parameters and other parameters. I'm not going to explain anything because it's not the point. The thing is we arrived at a very complex formula with lots of parameters to marginalize over, but still you don't have to worry because the computer does that. So even things become even more complicated later on. In the end, and I'm going to explain all the maths because you know more than me, what happens is something very surprising, which is this. These are my, if I use prior probabilities as flat, my posterior probabilities are almost the same. Then is when we start to think, wait a sec, so all softwares in the world, they just give you the maximum posterior. Kind of forget about this configuration. This is the most likely configuration. Forget about the rest, and we're going to continue the whole analysis only considering this kind of situation. I don't think this is the right way. We have to start to think along the lines of marginalizing over all possible models. Because we don't know that if this would be 0, I'll be happy. So that I can discard this possibility, right? But this is not 0, this is 0.49, and this is 0.51. So there's almost the same probability of being true. So then I have to keep these in mind in the further steps of my analysis. So how much I have of peak B, how much I have of peak A is not this solution, it's this solution and this solution all together. That reminds me, these numbers a little bit like what happened with the Brexit. So maybe in democracy in the UK you can think also along these lines, saying maybe instead of taking just one decision and forget about the rest, you can consider both at the same time. It's almost the same numbers, right? So these posterior probabilities remind me something. Doesn't matter.
The Americans are asking about today's election.
Yeah, okay, yes, that's going to happen.
Can you give us the numbers?
So we can give Hillary and Trump here also the same. So again, the same way of thinking that we're trying to push in our team is saying, can we start to think Bayesian at these levels? And sometimes even that forces us to think along the lines of marginalizing not only about different nuisance parameters, but marginalizing of different models that describe my data. And I think it's clear from here that these two models are almost the same. So then we just have to consider all of them at the same time. This is not what the software does. I insist on that. Software just cuts at certain points, say that's the most likely probability, so forget about the rest. Even they don't think in Bayesian terms, you just do some sort of peak detection, who cares? So, more things that we have been involved with is about analyzing samples from toxicology labs. So there is a dead body or something that has happened. We want to analyze certain lists of, in fact, 500 forbidden compounds, basically, in a sample. There has been a collaboration with the Dutch Forensic Institute here, and we do that via LCMS. For the people that is not mathematician, that is not chemist, that does not know what LC is, liquid chromatography. So we have this liquid sample, for example, a sample of blood. We pre-treat that. We analyze these via liquid chromatography. So all the compounds that are in the sample get separated in terms of different polarities or different chemical characteristics of the sample. And then at the end of this process, we analyze them via mass spectrometry. So basically, this is sort of way to analyze the sample. We have a very long signal that contains some peaks, and then we try to analyze, is a certain compound present? Is caffeine there because this guy was drinking too much coffee, so that's why he just gets fainted? Or is there rest of alcohol or metabolites of alcohol or cocaine or heroin or drugs or forbidden compounds? So it's a list of 500, and we do screening there. So what we did was again changing or shifting the way we think along the software that analyzes this sort of data. Normally the software analyzes this sort of data. They know where the compounds are going to appear in terms of the rotation time, so how long does it take for the compound to travel through the column, and also in terms of the mass of this compound, because this is analyzed via mass spectrometry, so we know certain compound what's going to be the mass of these compounds. For example, caffeine weighs 250 something. So, but all the software think along the same terms, saying the compound was there, the compound was not there, and do not give us any probability whatsoever. We thought that we could change the way of thinking, saying, okay, can we think in a Bayesian way, what's the probability of a certain peak feature of a certain compound being there? And in fact, just have two hypotheses. The peak feature is present, the peak feature is not present. We changed that question later on for the compound is present, the compound is not present. I'm going to explain that. And very simple, again, looks simple. That's the odd form of Bayesian theorem. These likelihood ratios start to grow because we have to marginalize over lots of parameters there. But some nice concepts arise that are very interesting from a chemistry perspective. For example, imagine that I have a certain compound that I know where the compound is going to be because I know the mass, but I have some doubts about the mass. So having doubts about the mass is a way to express a Bayesian prior about the position of this compound. Having some doubts about where the compound is going to appear in time, in rotation time, is a natural way of thinking in a Bayesian way, because we know that, we chemists know that certain compound like caffeine may appear at 20 minutes, plus minus 5 minutes, because we know that every time that we repeat the analysis, it's going to shift the peak. So we have sort of prior knowledge about where the peak is going to appear in these two dimensions, right? And what we discovered is that that fits very naturally in a Bayesian way. In a Bayesian way of thinking, this is my prior knowledge about the position of the peak in terms of the mass and in terms of the time. So we have certain uncertainty in rotation time, we have certain uncertainty because that's the resolution of my mass spectrometer, so things may appear at a certain point here or maybe there or maybe there. This is kind of area in which the compound might be. We also have to add okay, we added twice these because we want to make sure that maybe the compound might be there. So that's the area that I analyze when I have a compound. And we go to the mass, that's very simple. So we have to marginalize over the position where the peak alludes, and also we have to marginalize over whether we have one peak or two peaks. We can have different situations there. So that's another parameter, a nuisance parameter that we marginalize over, that contains other characteristics apart from the rotation time. So what I want to express here is that it's a very natural way of thinking for a chemist to say, I don't know where my peak is going to appear. And that's a nuisance parameter that we can use here to calculate this likelihood, basically. Okay, so for a lab clinician, like for example John, that is working at NFI, it's very easy for him to think, okay, do you know where caffeine is going to be? He's going to tell me 19 minutes, plus and minus 2. Okay, that looks like a Gaussian. So can we express your degree of belief about the position of the caffeine in terms of a probability distribution? Yes, very easy. Okay. So even some also elegant tricks that we can use there is merging evidence. So in fact, we can use the evidence of the data, the most abundant isotopes. For the people that is not chemists, isotopes are the different natural abundance elements that we can have in the periodic table, and in the mass spectrometry they appear at different positions, of course, and we can merge the evidence of the most abundant isotope with, for example, what is the aspect of the isotope ratio that we found. We know that, for example, carbon has a certain natural isotope ratio, carbon 12, carbon 13. We know that is the data, what is the probability of finding these data in terms of the natural isotope ratio that we're going to find. Or if it's something else, that might be a flat distribution. But here we know that if the data that we're looking for is caffeine, we know that the isotope ratio of caffeine is going to have certain values. So we can calculate this probability quite easily, basically. So when we plug in everything, then we have to just compare these with the software that is in place in the labs, and we have a problem because we cannot really compare. Any software that is in the labs, they don't think Bayesian. They just give a table saying caffeine is there or caffeine is not there. You cannot ask them, what's the probability of caffeine in there? No, it's a yes or no, a green or a red. But it's simple. We are producing something else, we are producing a probability value. So we had to convert that into a frequency table. So the only thing that we had to do is to set the threshold saying 0.5, for example. So if the probability of my posterior is above 0.5, I'm going to declare this as yes, as a green, or as compound is there. If the probability is below 0.5, I'm going to consider this as not present. The only way to compare this with a table saying yes, no. Okay. Of course, I can set up different thresholds, so I obtain a ROC curve. But when we are comparing these with, for example, Mass Hunter is a software, commercial software from an instrument manufacturer. We arrive that the performance of our method is better. We think that the reason for that is the fact that we are able to merge evidence in a more elegant way, because these software, we don't know how they work exactly, but we suspect that this software suffers when they try to merge evidence from different evidence. So isotope ratios, also the things that happen in a chromatographic column is adducts. So we can have a compound that can be an adduct with, for example, sodium, or an adduct with potassium, or an adduct with hydrogen, or different types of adducts may appear there. So we know, because we can model, how is the tendency of every compound to have an adduct with sodium, for example. So these also can be modeled here. All this information is plugged in very elegantly in the Bayesian equation. So we arrive to better performance compared to commercial software.
Is there some new data that you've tested it?
No, that's a very good question. No, we trained these adduct formation with calibration data, and we tested these with validation data, which is different.
What different?
It was different.
Can I follow up? Did you do a match study where you sent the same samples through both systems?
No, that's a very good question. The system was the same, yeah, but the samples were prepared differently, and we split them 50-50. But that's a very good question, because these values might be optimistic in terms of we have been overfitting just that system. So there's a warning there saying when you change the system, you need to remodel. Yeah? Or you may say my prior information about the adduct formation is less informative, so we have to flatten these priors because we are not that sure that this situation is going to repeat in another system. That's a very good question, yes. But within the same, because this is also tested within the same data, we are having higher performance. So the way to answer the question is, if these will be overfitted, these also will be overfitted. So it's a comparison of the same scenario. Still, there is a warning there, and I agree with you that you have to be careful when you change the system. You need to remodel that. But that normally happens because when at a certain point, when you have an instrument that drifts a little bit over time, you need to remodel this. Say, I'm going to recalibrate that system. I'm going to inject samples where I know what I have, so I can recalculate what is, for example, the tendency of adduct formation of all my samples. So I update my prior distributions for all these nuisance parameters. But it's a very interesting question, I agree with you. We extended recently these to LC-MS-MS. For the people that is not chemist, MS-MS is saying, so we separate a molecule inside a chromatograph, we analyze them via mass spec, and we take one isotope of this mass spec, and we break it into pieces, so the molecule breaks into pieces, and we analyze the fragments. So that's a lot more specific because there are not too many molecules that are going to give the same type of fragments, but still is going to have isotopes or isomers that give the same fragment. There's new information, which is the fragment parent to fragment ratio. So we know the amount of parent, we know the amount of daughter. Parent and daughter is saying the molecule that is analyzed in the mass spec is selected and then is broken because we give some energy to the molecule and breaks, so then we analyze also the fragment, and that ratio of the amount of parent and the amount of daughter is something that we know, it's something that we can model.
What is adduct? You used the word many times, but you never said what it is.
Adduct is, for example, a molecule to be analyzed via mass spec has to be ionized. Mm-hmm. Okay, suppose I have caffeine. Caffeine is easy to ionize because it contains a nitrogen, but to be ionized can be ionized with hydrogen there, or with sodium there, or with potassium there, or with ammonia there. And inside the system, and it depends on the system, there's certain tendency to be ionized with one of them, or with all of them. So it's a discrete prior distribution. We have, for example, 4. We know that for caffeine is very, very, I'm just making it, it's more affine to be ionized with hydrogen. So the probability to find hydrogen adduct is higher than to find a sodium adduct or potassium adduct, so on and so forth. Okay, all these can be modeled, of course, and every molecule has different tendency for the different ions because it's different of different nature. So as you can see, there's a soup of chemists and mathematicians and artificial intelligence people behind this type of project. So there's something that appeared here that was very interesting that made us reflect a lot, because all software, again, they do not consider what is in the denominator of the likelihood equation. So basically, how informative is my analysis depends on how many isomers may I have in the denominator of the likelihood ratio. So basically, if I see a picture of you, this is how I analyze things in the labs. I see a picture of you, say, okay, are you in the room? Say, yes, depends on how many twin brothers you have. Because I can see a picture of you, but you could have a twin brother, I could be in the room. So how informative is my likelihood depends on how many twin brothers you have. In the lab, something similar. So a molecule can show up the same mass, but be an isomer. And depends on how many isomers may I have for the same molecule, that has an impact of how rare is my likelihood ratio. So that has an impact of how informative is my analysis. You have something which is a lot common, a mass that is very, very common, that lots of molecules can show exactly the same mass, that's less informative compared to a mass that doesn't have any isomers. Okay, so these concepts of rarity appear there quite naturally. It's something that you use a lot in forensic statistics and appear here in LC-MS and LC-MS. More things that we did is when you have a mass. You have a mass of people, you have a mass of samples. Some people know, in fact, in the Netherlands, there was a project with the Dutch Forensic Institute. Some people know that you can dump illegal stuff when you have a matrix that has a very complex nature. So basically, you have these cells that you can dump in the environment. But some people use these to say, I'm going to smuggle extra things in these complex matrix and nobody will see. Because the matrix is so complex that you don't see what's there. Okay, that was a project together with the Dutch Forensic Institute. So basically, we have my original matrix, again analyzed via two-dimensional gas chromatography, and my original matrix with some extra compounds added. And the question is, can you see the difference between these two pictures? As looks like when I was young, I liked to see, oh, there's a difference. Yeah. But the problem is that...
But only pot.
The
Yeah.
buttons on
Yeah.
the shelf. The buttons on the shelf.
Yeah, you can see the spot. But the difficult thing is that you have to do these 750 times, because there is one of these pictures per mass. So you have to discover the differences in 750 pictures like that. That's too expensive. Okay, we need a method that is able to calculate these differences and highlight these differences. So you can see, for example, here this is an area here that I just highlighting. There is no difference. This area of this chromatogram is exactly the same as this one, almost the same, so there's no difference. If I look into here, there is something different, so there might be some extra compounds have been added here. Okay, but this has to be done 750 times because we have 750 of these pictures, one per mass that we analyze. So what we did, and again I'm sorry I'm skipping lots of mass there, is to look at tiles and to calculate the Jensen-Shannon divergence in these tiles, and we modeled the Jensen and Shannon distribution of these tiles, and we calculated the likelihood ratio of these distributions basically. So for every tile we have a value of the Jensen and Shannon, and we just calculate the likelihood ratio because we know the probability distribution of the Jensen and Shannon under the two hypotheses being one is saying things are the same, the other is saying things are different. So in the end we arrive to a log likelihood ratio map. So when things are very blue, it means that things are very different. When things are very yellowish, it means that things are almost the same. So this is a way to highlight where are these differences. And in fact we knew, because we just made the test, so we knew the sample, we knew what we added, we know what's in there, and that was a fantastic way to highlight the bluish part. So where are the points that are different. So it's an automatic way to highlight differences 750 times, all at the same time. Okay, so again this is not used in court, but it's more in intelligence, so in a forensic context. So it's a way to calculate to highlight differences into samples. It doesn't go down to court because it's just a way to highlight, to help the user, to help the lab expert in terms of analyzing differences like that. That's too manual, so we do it now automatically. So I think I'm going to take a shortcut. I'm running late, so go straight to conclusions. Sorry, yes, that's my shortcut. So I'm going to just one take-home message here, not going to be very complicated. So can we take Bayesian framework way of thinking earlier in the process? Can we start to think Bayesian from the raw data instead of from the pigtail? So we have to consider multidisciplinary nature of the process, because we know that we need chemists, we need signal processors, we need mathematicians, we need everybody together in this sort of soup. And at least, I don't know if Marjan can say, it has been a lot of fun to put all these people together. We had some very nice discussions in front of blackboards and whiteboards and whatsoever. So, just want to thank the team I belong to, Universiteit of Amsterdam. Also Marjan Lopatka, he could be in the audience, but he sent a message today that he couldn't be here. But our Dutch Scientific Council for funding, and also the Dutch Scientific Council for funding of another project of Michael and Andrei. And thanks for your attention.
Any questions? I just have one question. When you showed the sort of the crux of your talk was when you showed the peaks and all the different ways of drawing them, and then you should compare to something called Mass Hunter,
Yeah.
which is what people do generally, taking the most likely peak and just working with that
No,
one.
the Mass Hunter is the name, the commercial name of the software.
I understand, but their process is to take the most likely peak and just work with that one.
We suppose they do that because we don't know. They don't reveal how they do that.
Roughly my question was how much extra work is involved in the Bayesian thing than in what they would be doing.
Oh, once it is modeled, it is the same amount of work. The difficulty is to model all these prior distributions of the nuisance parameters.
But is it feasible?
Yes, because as long as you have several samples that you use to model this, it's all automatic in the software that we have constructed. So basically, you say, I know the compound is there, this is the sample. I know the compound is not there, this is the sample, so on and so forth. And okay, the more data you have, the better, because then your prior distribution is going to be better defined. But once this is modeled, it is the same amount of work.
So one needs a kind of a meta-analysis to compare to what extent the improvement you get from Bayesian analysis is worth it by being able to compare how much calculation time it takes.
In terms of computing time is around the same.
So that's okay. So that's
In terms of computing time, for the sample, once this is modeled, for the sample is around the same.
good.
It's 2 minutes to calculate these 500 compounds. There might be like 1 minute with a Mass Hunter. For me, it is not
It's
really
hard for us to
difficult.
tell when you say you have to do this 750 times. It's hard to tell whether that's a lot or not. 750. It depends what you're doing. It could be-
No, so the last one, the 750 pictures, that's also maybe 5 minutes
Yeah.
of a crappy computer. So computers are. This is a crappy one.
David?
So just to pick up on that point you just raised then, this Mass Hunter, you said you don't understand what it does. So do you think, is that generally the case that nobody understands?
No, I don't say I don't understand.
But I mean,
Nobody reveals
Yes.
how exactly they do it because it's a proprietary from the company.
And is that used as evidence in court without anybody having
I
a
suppose
detailed
so,
understanding of the...
because this is commercial software. So you purchase an instrument with the software associated with that, and we want to see where this peak is there, and the software puts some threshold and says when the peak height is above certain threshold, I declare the peak found. When the height is below a certain threshold, I declare the peak is not there. And it's also responsibility of the lab technician or the forensic expert to set up the threshold in a correct way. But setting up thresholds is taking decisions too early. Our approach is forget about the threshold. Let's consider the peak being there using these raw data. Let's consider the peak not being there using these raw data. What's the likelihood ratio of that?
You had one?
Yeah, just a technical remark. About the chromatography, you said that there was a time jitter due to many facts, I think.
Yeah.
Okay. Is it possible to make a real-time intercalibration in order to reduce it? Sometimes inject some known compound?
Yes, it has been done, but it brings more problems than solutions, basically. Because what happens is that we have 500 compounds, and every compound move differently. So if you have one reference compound per every compound that you have, you need to inject 500 extra. That's not practical. If you use just one compound as a reference, then the movement of every peak, it is on its own, so you don't solve too much. It's done in the mass domain, so in the mass spec, they use calibrants because they need to calibrate on the fly every single second where the compound is. So they have a reference there all the time. But in the chromatography, it's not done because of this reason, because everybody moves in a different way.
One last one, Jeff. I think you had one.
I think in the interest of time, I will
Okay.
ask that later.
Okay, well, thanks, speaker again.